I'm out here in the garage today because I wanted to test out a couple of the cool sets that I got from eBay last week, I guess. I got an AtariLab starter set with the temperature module, and I got the AtariLab light module. And both of these, as far as I can tell, have never been used. The boxes are a little beat up because they're from 1983, but generally they're in pretty good shape. I mean, there's a little bit of damage, but not too much. All of the contents are there. Especially this temperature module looks like it had never even been removed from the box, removed from the package. So yeah, I think we'll give that a try, see if it still works after 35 plus years, and maybe we'll go through a couple of the lab exercises and see if it's still possible to do any science with these things. I'm out in the garage now. It's extremely hot. Hopefully we will get some kind of results with this. I know the computer works. This is the Atari 800 home computer. For anyone who doesn't know, after the 2600 became a big hit, Atari developed a line of home computers. They were not as popular as the 2600, but they were pretty popular as home computers, 8-bit starter computers back in the late 70s, early 80s. This hardware was designed in, I don't know, 1978. These were released in 79. They lasted more than 10 years. I think they were still producing these into the early 90s. So let's fire this TV up here and see what we can get. Set these aside for now. Pop the covers off. If you've never seen an Atari 8-bit home computer, this is the 800 model, and I have a disk drive attached. We're actually going to be running software on cartridges, which look like this. It's got the nice 70s aesthetic going on there. Let's make sure that everything's set up and working here. Okay, so it boots. What I'm going to do is I'm going to open up the starter set with the temperature module, and we'll see how things go here. So I'll go ahead and show you what's in the box. We get a couple of things. One of which is the AtariLab starter set temperature module lab exercise book. This has instructions. Has a number of different classroom exercises that you can use with the sensors. You can do some experiments. It has graphs in the back where you could either copy this or write directly in the book if you wanted to. I don't want to. This book is mint, so I don't want to write in it, but we could always copy off pages and graph things on there. Talks about the interface, how it works electrically. There are some basic programming language programs in here somewhere that show you how to incorporate the output from the sensors into some programming that you might do. So it's kind of cool. And you can tell that they spent a lot of money on this. I mean, this is a very high quality book. Nice graphic design. Developed by Dickinson College. They had worked with a professor at Dickinson College by the name of Priscilla Laws. She was, I believe, a physics professor there. She retired a few years ago. She did a lot of this type of thing. A lot of her research was involved in how to use computers in the classroom to do science, primarily physics, but seemed like a pretty cool person. I was able to find a little bit of info about her on the internet. She's like I said, retired now, but She was the primary driver behind all of these. The AtariLab was the first set that she developed. There was another set almost identical, besides the hardware being a little bit different, that was developed for the Apple II computer. It came out after the AtariLab, and then they did a version for IBM's that I found, if I remember right, maybe from Wikipedia, they said that it was a common piece of classroom lab equipment well into the 90s. So they sold Atari didn't sell a whole lot of copies of this one, but this lab set in general sold quite a few copies and was used in classrooms. So let's take a look at what else we've got here. We have the AtariLab temperature module cartridge. We have a mercury thermometer, and it's very warm in here. It looks like it's about 88 degrees out here in my garage. We'll see how well that matches up with the results we get from the AtariLab temperature module. We have an AtariLab interface, which plugs into a joystick port, and then this is the sensor itself. So I'm going to leave this in the package. It's taped in with a piece of very yellowed tape. I'm just going to leave that there. But let's fire up the cartridge and see. Make sure that it actually works first of all. So we put the cartridge in, close the lid. Whoops, what am I doing wrong here? I need to reattach this piece. It's gotten kind of loose in its old age. There we go. And we fire it up and let's see what happens. All right, it works. AtariLab temperature module software, 1983, Dickinson College, Carlisle, Pennsylvania. All rights reserved. For keyboard input, press any key. For joystick input, plug a joystick into jack 1 and press the red button. Well, let's do that since I happen to have the classic Atari joystick right here. We'll try this out and see how it works. Awesome. Okay, so it's working. Now we have some setup instructions. Plug in the sensors. Plug the AtariLab interface into controller jack 2. This is the AtariLab interface. Goes into jack 2. Oh, okay. We've got a check mark. Plug the blue sensor into the left paddle input. I assume this is the blue sensor. As you can see, this has never even been opened. It's still got the little cable tie on there. I'm going to see if I can get this out of here without undoing the tie, because I'd like to keep this as pristine as possible. Yeah, I think we can make this happen. Okay, plug the blue sensor into the left paddle input right there. And we get a check mark. That's good. We got power. As I understand it, this basically breaks out the 9 pins of the joystick ports into individual interfaces that you can use with different pieces of equipment. There is 5 volts coming out of the joystick port, which they are using here to power an LED, but it looks like these are probably also 5 volts in case you need those for an experiment. I don't know exactly what they intend for control and P-trig. P-trig is the paddle trigger. Normally, if you would use, if you had paddles, which is what the rotating knob like that you would use for Pong, these joystick ports support what they call paddles, which is basically a potentiometer and a button. So the P-trig, I assume, is the button that attaches this line to that button line on the joystick port. The paddle is for the potentiometer. So it looks like we're going to be using the potentiometer input to get some kind of a reading out of this probe. What I'm interested in seeing is that knowing that the Atari computers of this line were 8 bits. That means we get 256 values. Unless they've done something that I can't imagine what that might be, I think that this is probably only 256 values of sensitivity, which means I don't see how they could have done tenths of a degree. I'm guessing that it's probably, everything's probably rounded to the nearest degree, and you have a series of degrees that it can register. But I don't know. We'll have to see how it goes. That's what I'm guessing, but we'll see how it goes. All right, step 3, optionally plug the orange sensor into the right paddle input. We don't have an orange sensor. I assume that's for a second temperature sensor. We don't have that right now, so I'm just going to press the red button, and here we go. Okay. So, setup experiment, bulb, demo, calibrate. I'll just go with the demo and see what it says. Okay, temperature, we're at about 31, 32 degrees Celsius. I'm hoping that I can convert this to Fahrenheit. I know that's bad, but it'll give me a little bit better understanding what kind of temperatures we're looking at. Oh, I see. Okay, so this is running an automated demo of collecting data and making a graph out of it. So that's kind of cool, just to give you a kind of an idea of the capabilities. Press button for menu. Okay, so calibrate bulb demo. Let's try bulb. Okay, this is giving us a thermometer. Press start to record, push button for menu. Okay. Oh, here we have Fahrenheit degrees. Yeah, it's about 87 degrees Fahrenheit in this garage. And it's very warm. I apologize if you see me sweating. But this is the best place to do this kind of thing out here in the garage. And this is where I have my monitor and my Atari set up at the moment. So you may notice I also have an Atari disk drive hooked up to this computer. It's on and running. We can use this, according to the back of the box, we can use this to save our data. So that might be an interesting experiment to try here. But let's go back to the menu and set up an experiment and see what happens. Choose Celsius or Fahrenheit, so let's do that. Scale is currently Celsius. Scale is Fahrenheit. Okay, that works. Choose time. Time is 10 seconds. I assume it's going to take measurements at every certain interval. Choose time. Okay. Oh, I see. Okay. So we can choose anything from 10 seconds up to 1 minute to 30 minutes to an hour to 24 hours for it to collect data. So let's start out with 1 minute. And actually, you know what? That may be a little bit too much for a video. Let's do 30 seconds and see how it goes. There we go. So begin experiment. Let's just try it and see how it works. Press button to begin. Okay, so here we have our graph. I think I'm going to try to influence the temperature just by holding on to the instrument. We'll see how it goes. Press button to begin. Okay, we're recording now. So we'll see if the temperature is rising. Yeah. So this is working. Yep, temperature is steadily increasing. Okay, press button for menu. Now let's see what we can do with this. Display data. Okay, so now we have options to see the table, print. Okay, if we had a printer hooked up to this, I don't have a working printer right now, so we'll have to skip that. Save data. or see graph. Let's see the table to see what kind of... Okay, so we can see it collected times 60th second, Fahrenheit degrees. So I think I was correct. As far as I can tell, this is capturing data to the nearest degree. So this is not going to be super useful for, especially for doing real science, but for a laboratory, if it were the early 80s and an 8-bit computer is what you had, sure, probably capturing the data to the nearest degree will let you run the experiments that they have in the box. But that is a drawback of this particular setup, is that it's an 8-bit computer and they don't have such a wide range of values that they can capture. Let's see how it goes. Okay, so we can see the 240. This is in 60ths of a second. So we can see as it goes along here, it did capture the temperature data. So as far as I can tell, it's working. We could do a little bit of an experiment. I have a cup of water. We could put some ice in it, see how that goes. Yeah, so I can cycle through. Temperature changed from about 87 degrees up to about 94 just by me holding onto the thermometer. So yeah, and then we could save the data. Let's see if saving the data works. I'm curious. I didn't have the drive turned on when I turned the computer on, so we may need to do something a little bit different to make this work, but we'll see how it goes. Okay, save data, data to disk, drive 1, temp_.dat. Type the file number and press return. Oops, we'll call this 01. Nope, we cannot do that. We'll call it temp1. Press return. IO error 130. Okay, so it did not work. I probably need to have the drive turned on when I fire up the cartridge because it didn't recognize the drive. Hopefully that's the case and not a drive going bad. But yeah, it does seem to work. I think what I'll do is pause the recording, get some ice cubes. We'll try one of the experiments in the manual and then see how that goes. Okay, I'm back. I now have a glass of water. I've been letting this get to room temperature for a few minutes. I have a tray full of ice cubes that we can experiment with. And I have my temperature set up, which I'm going to try to carefully remove this so that I can get a little bit more slack in the instrument here. There we go. Now that'll reach. So press button to go back to last menu. Okay, so we'll begin experiment. Press button to begin. Oops, I think I hold select to stop. I want to stop. Go back to the menu. I need to set this up first. Okay. Oh, you know what? There's audio. I can hear it slightly. I didn't even turn the, Yeah, there we go. There's actually a little bit of audio to this. Cool. All right. So let's just look at the bulb, what kind of temperature is coming out of this. And we'll test the temperature of the water here. Just see what kind of a reading I get. Oh, and it's dropping immediately. Okay, so it's gone down to about 79, which is actually a little bit lower than room temperature. But again, this is good. This tells me that it's working. One thing I forgot is a cloth. So this is probably not the best way of doing it, but all right, so let's go back and set up an experiment. And we'll test, let's say, I think one of the, I looked through the lab manual, one of the first tests that you can do is cooling down a glass with ice. That's not the experiment itself, but let's choose a longer time period, let's say 10 minutes. I'll let this run and I'll speed this up in the video. Okay, so I'm going to drop that into my water. Press button to begin. Okay, so we're getting some temperature readings now. It's about 79 degrees. Let's see how it works. I'm going to drop some ice cubes in. Yeah, so we're definitely getting some pretty good cooling, as is to be expected. Seems that there's nothing wrong with the AtariLab interface, the temperature sensor, the experimental setup seems like it's good. There is an interesting project that we could look at. Chapter 3, Project 4, Keeping Your Soda Cold. When we want a hot drink on a when we want a cold drink on a hot day, we add some ice cubes to the drink. After a few seconds pass, we should have a cool, refreshing glass of iced tea or lemonade. How does ice cool liquids so well? We depend on the cooling effectiveness of ice to prevent foods from spoiling, as well as to cool our lemonade. In this project, you will learn about a concept known as latent heat of fusion. It will help you understand why ice cools liquids so effectively. Purposes: to review Newton's law of cooling and warming, to learn about the latent heat of fusion stored in ice, to use the law of cooling and the idea of latent heat of fusion to answer a practical question. The equipment and materials we need are an Atari laboratory station, 8 ice cubes, 2 8-ounce glasses, not styrofoam, room temperature water, a large cake pan or tray. So I believe I have most of that except for the cake pan. I could go in the house and grab one, but let's see what we're trying to answer here. Suppose you have a party planned and you want to serve cold drinks to your friends as soon as they arrive, only 10 minutes from now. In front of you on the table are several glasses of room temperature soda and a bowl of ice cubes. It's a hot day and you'd like the drinks to be as cold and refreshing as possible 10 minutes from now when they are served. Should you add the ice cubes right now? Or should you add the ice a couple minutes before serving the drinks? Can you design an AtariLab experiment to answer this practical question? Before devising an experiment, let's consider some more about the theory of heat energy absorption and the flow of heat energy between ice and air or water. Perhaps we can develop a hypothesis which will allow us to predict the answer to this question. A hypothesis, remember, is a statement that identifies general relationships between characteristics, properties, or events observed in nature. So then we go on, we talk about the background on heat energy in ice, talking about changing from a solid to a liquid state. When an ice cube at 0 degrees Celsius is placed in warm water, it will cause much more cooling than an equal mass of water at 0 degrees Celsius. You can easily set up an experiment to show this. When the heat energy from the liquid is absorbed by the ice, most of it is needed to break the solid bonds which keep the ice molecules bound closely together. This allows the ice to become a liquid. Once enough energy has been provided to break the bonds between the ice molecules, any remaining heat energy is transferred to the melted ice water. This energy goes into increasing the speed at which the water molecules slither past each other. The heat energy needed to change ice at 0 degrees to water at 0 degrees Celsius is known as the latent heat of fusion. Ice cools liquids effectively because so much of the heat energy in the liquid goes into melting the ice before the temperature of the melted ice can be raised. This loss of heat energy in the liquid surrounding the ice causes the liquid to cool off. So this is kind of interesting. I'm sure I probably learned this at some point in middle school science, but I don't remember the specifics, to be honest. A hypothesis that predicts the best way to cool a liquid. So we're developing a plan to test the hypothesis, testing the cold soda hypothesis. You can take 2 glasses of room temperature water, or soda if you like, and record temperature changes in one glass for 10 minutes when you add 2 ice cubes to it right away. You can then record the temperature changes in the second glass for 10 minutes, but wait until 6 minutes have passed before adding the ice. So then there's some experimental setup. Doing the experiment trial 1, adding the ice immediately. We have some sheets for recording our data. Questions and conclusions. Which method works the best for keeping your soda cold after 10 minutes? Does the hypothesis seem valid? You might try this activity. Suggestions for other projects. You might try this activity with a liquid other than water, such as fruit juice, soda, or milk. What happens if you start out with a liquid at refrigerator temperature rather than room temperature? Suppose you use much more ice and it doesn't all melt at the end of the 10 minutes. What happens? Styrofoam cups are insulated so that they keep the temperature of the liquid inside fairly constant. Cold drinks stay colder and warm drinks stay warmer longer than in an ordinary cup. Try using styrofoam cups and compare the results. Okay, so we're getting some data here. It seems like the cooling all happens very quickly. So I think that probably the first hypothesis, that if we had waited until 6 minutes, if somebody's coming at the 10-minute mark, if we had waited until 6 minutes to put the ice in, I think that would have sufficiently cooled the drink. But without doing that second experiment, I can't say that for sure because we should do things using the scientific method. But yeah, we're coming up on 8 minutes of data collection here. And everything seems to be working fine. You can see that the resolution of this graph is not great. Keep in mind that we're using hardware that was released in 1979. But I mean, for the time that this came out, this would have been pretty cool to have in a classroom, I think. Considering that if you're not using a computer, probably the best lab practice then was to take this mercury thermometer and continuously dip it in the glass every minute or so and then graph it out by hand. I'd say that sitting here and letting the computer do that, run that graph, is probably preferable to the manual way, even if we're only recording things to the nearest degree, and the resolution of the graph is not great, but it does go into a screensaver mode after about 9 minutes. That's what we were seeing there. It cycles the colors so that it doesn't burn into the CRT. Yeah, this is pretty cool. I would have been into this in a science class. It's probably, I get the impression that these are designed. You know, we got a cartoon dragon on here doing the experiments. I get the impression that these are probably designed for middle school science classes. But I can imagine that I would have been into this in middle school, in a science class. Would have been fun to do this on the Atari computer. The other interesting thing is, here are the programs that you can write. Oh, there's the alarm. That means our data collection is done. So as you can see, most of the cooling happens in the first 6 minutes. Although now that I think about it, if we had waited 6 minutes, the glass would not have been as cool at 10 minutes. Our cooling basically evened out after 6 minutes or so. So to answer the question and to get the coolest drink that we could possibly have for someone who's coming in 10 minutes, you should probably put the ice into the water at the 0 minute mark rather than waiting until right before they get there. So yeah, I don't know that we necessarily have to do that second experiment because this kind of tells us everything that we need to know. So yeah, this is kind of fun. I also have the AtariLab Light module, which has 2 sensors in it. Well, it has a light emitter and it has a light collector or a light sensor. And then it has some other things like polarized filters and a box that you can insert the instruments into and get kind of a dark environment to block out ambient light. So yeah, this is kind of cool. And back to this, we have sample AtariLab programs in Basic and Logo. Logo was a very popular. Well, Basic was a lot more popular in the 80s than it is now. Basic and Logo was a graphical language for it was Turtle Graphics, if anybody remembers that. But this shows you how you can write software to take the inputs from the joystick ports and use those. So yeah, I mean, even in some kind of basic computer class back in the 80s, this would have been really cool. I don't think there's a whole lot of use for it nowadays. It's obviously been superseded. A whole lot of use other than historical curiosity, I should say. It seems like it's been obviously superseded by more accurate instruments and more devices with higher resolution, and it would be a lot easier to use a graphical user interface to store your data rather than using the keyboard to spit things out to an external disk drive and all sorts of things. But you know, I think this would have been pretty cool to have back in the 1980s in a classroom. I did see some anecdotal reports of teachers talking about how they did use this in their classroom in the 80s, and sometimes they had multiple Atari computers, sometimes they had one, and they would all just kind of gather around and run the experiments there. But there's a whole set of projects in here. Here's one on salt and ice. How does that affect the heat of when you put the ice into the glass? How does that affect the temperature curve there? Baking soda and vinegar. How does that affect the temperature curve? Measuring daily changes in air temperature. You saw that we can do these tests over the course of 24 hours. We could set this up, let it run, and see what the temperature is out here in the garage during the day. So yeah, this is very cool. I'm glad that I have this. I'll probably play around with it some more because I could definitely use a science refresher. It's been many years since I've learned even the basic science. So yeah, anyway, thanks for watching. I will have more Atari videos on my channel, so please like and subscribe, and I will see you later.